This is my second video in my module on finding the average of a probability distribution. Okay, and this is going to be a little bit more just run through the examples and talk about the reasonability of it later. But we'll start with this. We say the mean of a probability distribution, or at least a discrete probability distribution, is this idea of mu. Okay, so we say mu, the long-term average or mean of my probability distribution, is defined as being the sum of all of the things that could happen in the event space times their respective probabilities of it actually occurring. So this is the formula we anticipate using for these exercises, okay? So let's go ahead and take a look at three examples here, starting with number 2 up here. It says, in a family with 2 children, find the mean number of children who will be girls, okay? It says the probability distribution is shown below. So the number of girls we have listed here, we say if we had a family of 2 people, I suppose we could have a girl and then a girl. We could have a boy and then a boy. We could have a girl and then a boy. We could have a boy and then a girl in terms of the outcomes here. But basically we're saying we could have no girls, we could have 1 girl, or we could have 2 girls. And in terms of their probabilities, we say, well, the likelihood that I have no girls, well, that was just once. You know, I say this one right here, 1 out of 4. The likelihood that I get exactly 1 girl, well, you know, we had 1 girl born here and 1 girl born here, if I can draw this out correctly here. But basically 2 out of the 4 instances, we have 1 girl. So we say that's a half of the time. And then last but not least, the last 1/4 of our data set over here, or sample space, is essentially 2 girls. Okay, so we say if this is the case, we want to find the average. The thing we're going to do here is this: we're going to extend our table. We're going to add in this row down here, and what this row is a space for us to calculate all of everything that can happen times the probability that it does happen. So we'll label this. We say this is x times the respective likelihood that x actually happens. So for instance, we say 0 times 1/4, this would be 0/4. Or 1 times a half would be 1/2. Or 2 times 1/4 is 2/4, which by the way is the same thing as a half. A half. Try this again. A half. Okay. So what we're going to do is we're just going to fit this in over on the right side here, but we say the sum of all of these things that could happen times the respective probabilities that they do happen, we would say is this: we've got 0/4, which is 0, plus a half plus a half. So a half plus a half, we get 2 halves, which comes out to be 1. We're going to label this because x was representing something. It says on average, if you were to look at all of the families having 2 children on the planet, what's the average number of, say, girls you're going to find in the family? You say on average, they probably have on average 1 girl in every 2-person family, on average. It doesn't mean they do, just means that that's what is most typical when you have 2 children, okay? So remember, we think of this average of a probability distribution as being like a long-term average. That's what it is. It's a long-term average if you were to look at the data set for eternity, okay? So we say, all right, example number 3 here, it says, in the experiment in which 3 coins are tossed, find the mean number of heads that occur. I think it's going to be useful for us here to write out our probability distribution, but before doing that, actually coming up with a sample space. So for example, you know, we could flip 3 coins and get heads, heads, heads. Likewise, we could also get tails, tails, tails. But let's list out the other 6 possibilities. There are 8 total. We could say we get a heads, and a tails, so we could alternate this: a tails, and a heads. How about a heads, tails, heads? We'd also get a tails, heads, tails. And then last but not least, I suppose we could get just a head and 2 tails. Therefore, we have a tail and 2 heads. So this is our sample space right here. This is all the different possibilities that occur. We want our variable to represent the number of heads that can occur. So the first thing we're going to do is we're going to define this. We're going to say let x equal number of heads in our distribution here, okay? So in terms of, well, how many heads could actually pop up when you flip 3 coins? Well, I'm looking at this here, I suppose reasonable, you know, like, let's be reasonable about this. I suppose when we make our probability distribution here, if x represents the number of heads I can get when I flip 3 coins, suppose I could flip no heads. I could also flip only 1 head or 2 heads, and at most 3 heads, because I only flipped 3 coins. But essentially, these are all the possibilities. So again, to find the average, we're just going to build in this 3rd row right here. It's really easy to do. We say we'll take everything that can happen times the respective probability that it does actually happen. So we haven't found the probabilities yet. I suppose we should do that. We say, well, how many of these 8 over here gave us no heads? Well, we got 1 of them right here. We say, okay, well, that would be a 1 in 8 possibility. Okay. So now that we've accounted for that, how many of these over here had only 1 head on them? Okay, so we got 1 head here, 1 head here, oh, and 1 head here, okay? So we'd say this is a 3 in 8 chance, 3/8 of them had one head. Also, this has two heads on it, this has two heads on it, and this has two heads on it. So also 3/8 of the time we got two heads, and there was only one instance in which all three of them were heads, so 1 and 8. And of course this makes sense because all of these probabilities should sum up to be 1. But yeah, we're going to find the average now. We're going to take the sum of all of these things that can happen times their respective probabilities. So let's go ahead and multiply these. We get 0 times an eighth, which is just 0/8. I would encourage you to write 0/8 and not just 0. 1 times 3/8 is 3/8, of course. 2 times 3/8, well, 2 times 3 is 6. We get 6/8. And then last but not least, 3 times an eighth is 3/8. So summing all of these, we're going to find the average now. The sum of all of these, the products of things that can happen with their respective probabilities, we would get how many total 8s. So we say, well, 0/8 plus 3/8 is 3/8, plus another 6/8 is 9/8, plus another 3/8 is 12/8. So essentially, we put this into a calculator. Not that I need a calculator to do this guy, but I will, just to show you here. 12 divided by 8. We're going to write this down. We say 1.5, and just like we have in the past with averages, we should label this. And what we were keeping track of was the average number of heads that show up on a coin. So it's kind of like saying this: if you flip 3 coins, on average, how many heads do you expect to see? 1.5, which is weird because when one considers this, I suppose if we were to sketch an image of our probability distribution graph, we have like 1, 2, 3/8 here. Let me say 3/8, 2/8, 1/8, and those are all our probabilities that could happen. I use those because those were the ones that showed up over here. That's as far up as I need to go was 3/8. And we say, okay, well, we could get 0 heads, 1 head, 2 heads, or 3 heads. But when you look at the graph of this, we say we had a 1 in 8 chance of flipping no heads, 3 in 8 to flip 1 head, 3 in 8 to flip 2 heads, and then a 1 in 8 chance to flip 3 heads. So we say, well, what's the average? Well, if you look at this distribution, we say, well, where's kind of the balancing point right here? The interesting thing is you're right here. We say 1.5 heads. Now, the interesting thing is you can't actually flip 1.5 heads. But what this means is if we were to flip these 3 coins right here for eternity, and each time, by the way, as we're flipping these coins, we're writing down, I got this many heads, I got this many heads, I got this many heads. What we find out is this: if we were to keep track of all of those, add them all up and divide by however many there are, which we can't do because there were eternal amount of them, we would find that the average number of heads is 1.5, which is reasonable given that this is our distribution of our probabilities. Okay, so this last one here is kind of an irregular one. We'll look at one that doesn't involve coins or boys and girls. We'll take a look at something where maybe we actually keep track of the data. We have data on this. So it says the probability distribution shown represents the number of trips of 5 nights or more that American adults take per year. So essentially, we gave a survey. We said, hey, how many five night or more vacations do you take a year? And we found that, we say like zero vacations a year, 0 5-day or more vacations a year. 6% of our respondents say they never go on vacation. As a matter of fact, I fall into that category. So we say we have 70% of the people who responded said, yes, I go on 1 vacation a year. That's 5 nights or more. And then we had the distribution of these over here. 20% of people say I go on 2 vacations a year. Only 3% go on 3 vacations or more per year, or 3 vacations a year. And then only 1% go on 4 vacations a year. Man, I want to go hang out with these people. But essentially, I want to know, well, on average, how many vacations per year would everybody take? And I don't mean just a few people. I mean like everybody, okay? And we can actually find this. This is the wonderful thing about finding the average of a probability distribution. It is the average of everybody. It is the eternal average, the long-term average. So just like always, we're going to find the average by first adding in a row where we take everything that can happen in terms of vacations times the likelihood that they do. So for instance, 0 times 0.6, we're actually going to write 0 on this one because 0 times anything is 0. 1 times 0.7 or 70%, that's a 0.70. 2 times 0.20, well, that would double it, but 0.40. 3 times 0.03 would be 0.09. And then last but not least, we say 4 times 0.01 would be 0.04. So now we want to find the mean. Now this time I'm actually just going to write mu, okay, or mean, instead of having to write, hey, the sum of x times p of x. But they're the same thing. We say adding these up, let's see, 70 cents plus 40 cents would be $1.10. $1.10 plus another 9 is $1.19. $1.19 plus another 4 cents is $1.23. So we're going to label this. I always want to label. But basically, we say on average, the average, say, person that responded to this survey takes 1.23 5-night or more vacations a year. And that actually kind of is reasonable considering the fact that, hey, you know what, majority of people take one vacation, so of course our average would be close to one. But the rest of the people, we only had 6% of the people below this and the majority of the other people above it. So it dragged our average up. And again, if we were to look at the graph of this probability distribution, I suppose we can construct one over here. It's not going to be a very pretty graph because I don't have a lot of room to work with here, but I notice my highest probability is 70%. So I'm gonna try this out here. 1, 2, 3, 4. We'll call this 50% right here. And we'll call it 60 and 70 right there. Those are our top bar. And we say, well, number of vacations per year, it was either 0, 1, 2, 3, or 4. So if we were to actually draw on the bars that correspond to each of these probabilities, for instance, 0 vacations a year was about 6% of the time. So that's like maybe that tall. One vacation, oh my goodness, it was like 70% of the people responded with one vacation a year. So it's a very tall bar. 2 vacations a year, that's 20%. So that bar is like 2 of these notch marks over here. And then 3 and 4% are 3%, or 3 and 4 vacations are at 3%. Which would be half of this first bar, which was 6%, and 1%, which is this little hiccup over here. We say, well, where's the average number of vacations? Well, if I asked you to put 1.23 down here on the number line, we would kind of say, well, it's kind of like, I don't know, like right here. But if you look at the data set here, this is kind of like the balancing point for our data set. So we say the average number of vacations in the long term of everybody was about 1.23, which of course we acknowledge you can't take 1.23 vacations, but still it's entirely meaningful, that value. So that's how you continue to find means of probability distributions. Cheers.